with sufficient train. Okay. Now, another one is your optical sensor, and this optical sensor is commonly used for the measurement of displacement. Now, if you try to observe this optical sensor, if you see, here is the target, and this target is either moving forward direction or reverse direction. One power source is provided, then light source, which is operated using power source, then using transmitting fibers or optical fibers, that has been that signal light source is trying to move towards the target. And again, photodetector is used to detect the light which has been reflected from the target object. This photodetector will try, this photodetector will try to deflect the light from target, and signal processing will provide you the output terminal. So what happens, as your target is moving in the forward direction, x is nothing but it is the displacement of the target. If it is moving in the forward direction and your system of transmitter and receiver is at one fixed position, transmitter and receiver is at one fixed position. So when you are moving the target in the forward direction, you are making the displacement far away from transmitting and receiver one. So the time required to reach from your light source towards the target and again reflect back from target to receiver will be more, which is calibrated in terms of the displacement. Now, if we are moving the target towards the backward side, at that time, the distance or the displacement is minimized, and you people are going to get the fast response towards the detector, means your time duration has been minimized for this particular aspect. Now, here, when the time duration is minimized, the response which you are going to get, that will be the faster one. So the change in displacement of the target can be measured easily using optical sensors. So by processing it one. So optical displacement sensor works on the basic principle that the intensity of light decreases with either distance or increases with the reducing the distance. The light source could be a laser light, or it may be a LED, or photodiode, or phototransistor. And one of the example in recent days, as people are well aware about that COVID-19, some dispenser has been generated or developed, designed and developed, depending upon IR sensor, infrared light source. So here you people can use this optical sensors, and one of our students have developed also this optical sensor type of dispenser to deliver or to discharge the your sanitizer. So here practically we have executed using IR sensor, means that is also one type of optical sensor which has been fruitfully incorporated, considering the current scenario of COVID-19, to design an application of your smart sanitizer, that is non-contact type of smart sanitizer. Two types of sensors our student have used. One is the ultrasonic type of sensor, and another one is IR sensor. We people are having that particular models in our lab also of ultrasonic type of sensor. We are not having that ultrasonic optical type, but we can make it available as already students have developed. So this is real-time example for optical type, depending upon the displacement. You can easily monitor. So what should be the range? If you trying to bring it closer, then and then only you are going to get the output. These things are much more matters while designing any particular application. Practically, I will show this particular device working real-time development of these sensors or applications for smart dispensers. Then the another one is the Hall's effect. Similar to that of your inductive type of transducers, the Hall's effect was discovered in 1879 by Edwin Herbert Hall, and on his name, the Hall's effect has been working. So while he has developed this one, or he has researched this one, when he was pursuing his doctorate degree or his PhD degree at the Johns Hopkins University in Baltimore, Maryland, US. So he discovered 18 years before the electron. Means this Hall's effect was discovered 18 years before the electron. How this particular Hall's effect, I will even share you one PPT or a video on the Hall's effect. That Hall's effect is the production of a voltage difference across a current carrying conductor perpendicular to both current and magnitude. So what happens if suppose we people are having this is one of the particular field, or rather than that you can use the Faraday's law of electromagnetic induction to understand this particular concept. So in this one, what happens when a current carrying conductor is placed in a magnetic field, depending upon the variation in the magnetic field, actually the voltage or EMF is generated, and that EMF is proportional to the field across it. So when a current carrying conductor is placed in a magnetic field, a voltage will be generated perpendicular. So B is nothing but the voltage, magnetic field that has been generated perpendicular to both current and the field. If you try to observe, one is a blue line, one external power source has been applied to a plate. Then the reddish part is the voltage which is supposed to be measured, and the black line B is the perpendicular voltage or the perpendicular magnetic field which is generated. But when this is possible, when we people are applying the external magnetic field perpendicular to it, then and then only in proportion to that your voltage will be generated. So when perpendicular magnetic field is present, the Lorentz force is exerted on the electron. How it is exerted, I will show. Due to which electron moves in the perpendicular direction to both current and magnetic field and develop a potential difference across the conductor or semiconductor. Okay. So over here, I will share one